Okay, I want to remind you again real quick to be careful how you think about definite integrals. It's true that many definite integrals define the area of a region between the function and the x-axis, but not every definite integral gives you area. Consider if you evaluated this definite integral. Well, if you evaluate this integral, I'll let you to check my work here. But if I evaluate this definite integral, I'm actually going to get negative 15. Okay? And obviously negative 15 doesn't represent an area. Well, if you look at the graph, you'll notice that if you go from, if you take that function x cubed and you go from negative 2 on the x-axis over to positive 1 on the x-axis, which would be about right here, or right there where that line is, then you can see this function kind of breaks the rule for area. For the integral to represent area, remember the function has to be non-negative. Obviously the function is negative at points over that interval. So since that function breaks that rule, obviously this definite integral would not be something that represented area. Okay, pause the video here and then do practice on these 4 problems, and I've got the answers given to you on the right. And then when you're ready to check your answers, you can start the video back up and continue watching the video. Now, there's a mean value theorem for integrals, and it basically goes like this. If f is continuous on the closed interval from a to b, then there is a number c in the closed interval such that the integral from a to b of the function equals f of c times b minus a. So in other words, what they're saying there, if you think about that, b minus a is the length of the interval. So I'll show you the average value version of this in a minute, but basically we're just saying there's an average value. There's actually an average value, and that's actually what f of c represents, is the average value. But let me start you with an example of this. Suppose we have the function 3x squared and the interval is 1 to 3. Okay, so if we evaluate the integral from 1 to 3, 3x squared is simply going to be x cubed when we integrate it, and then from 1 to 3 it gives me 3 cubed minus 1 cubed, which is 27 minus 1, or 26. Now, we want to find c such that f of c times b minus a equals this integral, 26. So let's say f of c times b minus a. Well, b minus a would just be the top minus the bottom, so that's 3 minus 1, which is 2. So 2 times f of c must equal 26. So if I divide both sides by 2, then f of c must be 13. But now think about what is c. What is f of c? Well, what's my function? My function is, this function is 3x squared. So my function is 3x squared, so f of c would be 3c squared. So I want to solve c such that 3c squared equals 13. So that's a pretty simple equation to solve. So solve for c squared, you get 13 over 3. And then if you take the square root, now you're only going to want the positive square root because the negative square root is not in the interval. So we want the number that's in the interval from 1 to 3. So it would be square root of 13 over 3, or approximately 2.1. And there's a variation of this that's basically almost the same thing. There's a definition of the average value of a function. Well, if you can integrate the function f over the closed interval from a to b, then you can find the average value of f on the interval. Now, you might remember when you average something like grades, you have a finite number of grades, and you can add them up and then divide by the number of grades. Well, an integral is like an infinite sum. So it's like adding up infinite many values. But so what we have to do there to get an average of an integral is we have to divide by the length of the interval. So to find an average value, so if I want to find the average value of this function from 1 to 3, well, the first thing I got to do is I've got to evaluate the integral, which we just did. So we just did that, so I'm not going to do it again. And we got 26. So then we multiply by 1 over b minus a, or you could just say we're going to divide this integral by b minus a. So this integral equals 26, so we're going to divide this integral by 3 minus 1, which is 2. And so the average value of that function is actually 13. So that's the average value. And so don't get that confused with what we found earlier. Earlier, what I found was the number, was the functional value that actually gave me 13. So that's the difference between the two examples. All right, now this is an example that I found in a text, so I kind of changed it to my liking. So speed of sound. At different altitudes in the atmosphere, sound travels at differing speeds. So the speed of sound, we'll call it S of x, can be represented by this function below, and the units are meters per second. So basically we've got this piecewise function that's defined over 5 pieces. So from an altitude, x by the way is kilometers let's see, yeah, it's kilometers. So from 0 to 11.5 kilometers, the speed of sound follows this function. From 11.5 to 22, it follows this function, constant function. From 22 to 32, the speed of sound follows this function. From 32 to 50, it follows this function. And from 50 to 80, it follows this function. So what I want to do here is I want to find the average speed of sound over the entire interval from 0 to 80. Notice that I'm going from 0 all the way to 80, but I'm going through that through 5 different functions. So basically what I'm going to have to do is I'm going to have to evaluate each integral. So to find the value of the entire integral from 0 to 80, I need to evaluate each piece. So kind of like I did that absolute value function a while ago. So this first piece, I integrate the 4x minus 4x plus 341 from 0 to 11.5, and I'll let you do the evaluation, but I got 3657. And then if you integrate 295 from 11.5 to 22, I got 3097.5. And then I integrate the next function, and it says it's over the range 22 to 32. So when I evaluated that function, I got 2987.5. And then the next range of altitude is 32 to 50 kilometers, and I got 1.5x plus 254.5 for that function. And then when you integrate that, you get 5688. And then when you do the last one, that's negative 1.5x plus 404.5 from 50 to 80 kilometers. That one equals 9,210. Now, if you add all the integrals together, you get the total value of the integral, which when I added them together, I got 24,640. So now if I want the average value, I just divide that by the width of the interval, which is 80. So divide 24,640 by 80, and I got 308. And so the average value of sound over the altitude 0 kilometers to 80 kilometers is actually 308 units. Or actually the speed of sound, about 308 meters per second, I guess is what it was. Wasn't that what it was? Meters per second, yeah. So it's 308 meters per second. There is a second fundamental theorem of calculus defined like this. It says if you take the derivative of the integral from a to x, f of t dt, with respect to x, you'll get the function f of x. Now the reason that we're not using x in here is to avoid the confusion between the f of x here and the f of x in here. So basically the theorem it works looks like this. If you let f of t be 2t, well, if you were to integrate f of t dt from a to x, let's do that. If you integrate 2t dt from a to x, well, 2t integrates to t squared. And if you evaluate it from a to x, you get x squared minus a squared. That should be a minus. So you get x squared minus a squared. Okay? Well, we know the derivative of x squared minus a squared is 2x. But if we use this theorem up here, the derivative of this, based on that theorem, tells us that the derivative of this is just this function evaluated at x rather than t. So actually we can just evaluate that function at x to get the derivative of that integral. So let me show you a couple of examples. And it doesn't matter what this number is. It can be any real number. So if I integrate from 5 to x cosine t dt, and I want to take the derivative of that integral, then that's just going to be the cosine of x, because it's just cosine of t with t replaced with x. From 2 to x, t squared minus 1 dt, if I take the derivative of that integral, then I'm just going to get x squared minus 1, because I had t squared minus 1 in here. And then you can do the last one on your own and see that the answer is square root of x. Now if you're going from a to a function of x, you actually have to use the chain rule. So what we would do here is we would say we're integrating from 5 to x cubed cosine t dt. Normally that would be cosine of x, but in this case it's actually going to be cosine of u times u prime. So let's let u equal x cubed, which is what this is, and then u prime would be 3x squared. So anyway, and I think I meant to have just x here. So if you integrate from 5 to x cubed, then the derivative of that would be the same as the derivative of the integral from 5 to u cosine t dt, and that would be cosine u times u prime, and then cosine, and u is x cubed, so it would be cosine x cubed times 3x squared, or just 3x squared times cosine x cubed. Hopefully that made sense to you. Okay, there's a net change theorem here that says the fundamental theorem of calculus states that if f is continuous on the closed interval from a to b and f is an antiderivative f of ab, then we know this is true. But we could also write that if you integrate f prime of x dx, where f is the antiderivative, we get f of b minus f of a, where f of b minus f of a represents the net change of f on the interval from a to b. Well, so here's an example of this. An example: chemical flows into a tank at 200 plus 6t liters per minute, where t is 0 to 75 minutes. Find the amount of chemical that flows in the first half hour and the second half hour. Well, for the first half hour, your rate of flow is 200 plus 6t. So if you integrate that, you get 200t plus 3t squared. And then for the first half hour, we integrate that from 0 to 30. And you can go through the arithmetic there, and I got 8,700 liters. For the second half hour, I do the same thing, except I integrate from 30 minutes to 60 minutes, and then I got 14,100 liters. Well, actually, all you have to do to get for the entire hour is just add these two numbers together and get 22,800 liters. But if you integrate from 0 to 60, that same function, you're going to see that you do get 22,800. So the two answers do check. I'm going to throw this in quickly, but when calculating total distance traveled by a particle, you must consider the intervals where the particle is below 0 or velocity is above 0. And so let me go ahead and just show you an example. Suppose the particle is traveling on this path and from 1 to 5. Well, that function over here from 1 to 4, it's above the x-axis, and from 4 to 5 it's below the x-axis. So what you have to do to find the total displacement on 1 to 5 is you actually integrate from 1 to 4, positive the function, and then you integrate, and then you subtract from 4 to 5. That should say 4 to 5 instead of 1 to 4. Then you 4 to 5, so you integrate from 4 to 5, and then you subtract the two values, and you get the total displacement, which is 11.6 0.83. And that's pretty much all I have the time for, so hopefully you got most of that on that example.